Modules 3 and 4 each used a single monomer. Now we add a second. A new question follows. Once two monomers are mixed, what is the sequence of units in the chain? Random, alternating, or blocky? The answer comes from one pair of numbers, called the reactivity ratios. At each step in copolymerization, the growing chain end faces a choice. If the end is monomer 1, it can add another monomer 1, rate constant K11, or it can add a monomer 2, K12. Same for an M2 end. The reactivity ratio R1 is the ratio K11 over K12. If R1 is greater than 1, an M1 end prefers more M1. If less than 1, it prefers M2. Same logic for R2. Combining all four rate constants gives the Mayer-Lewis equation. It tells you the instantaneous mole fraction of monomer 1 in the copolymer, F1, from the feed fraction F1 and the two reactivity ratios. F1 equals R1 times F1 squared plus F1 times 1 minus F1, divided by R1 times F1 squared plus 2F1 times 1 minus F1, plus R2 times 1 minus F1 squared. The shape of the F1 versus F1 curve is the system. Four canonical shapes capture most behavior. When the product R1 times R2 equals 1, the system is ideal. Sequences are a biased coin flip. When both ratios approach 0, each end prefers the other monomer, and the chain becomes strictly alternating. When one ratio is much greater than 1, and the other much less, one monomer is consumed first, leading to blocky chains with composition drift. And wherever the F1 versus F1 curve crosses the diagonal, you have an azeotrope. At that one feed composition, the polymer composition matches the feed exactly. If the feed composition does not match the polymer composition, the feed drifts during the reaction. The faster monomer depletes first. Early chains have one composition. Late chains have another. The result is a mixture that looks like a single polymer but is really a gradient of compositions. Only at an azeotrope does the chain composition stay constant from start to finish. Let us compare two real systems, both at 50% feed. First, styrene and maleic anhydride. R1 is 0.05, R2 is 0.005. Both small. Predict. Strictly alternating. Almost no drift. Second, acrylonitrile and vinyl acetate. R1 is 5.5. R2 is 0.06. One huge, one tiny. Predict. Blocky chains with dramatic composition drift. Open the Module 5 notebook. R1 0.05, R2 0.005, feed fraction 0.5. Run all. The Mayer-Lewis curve is nearly flat near F1 equals 0.5. The bead visualization shows tight alternating runs of monomer 1 and monomer 2, and the drift plot stays horizontal. The chain composition does not change as the reaction progresses. Now change the chemistry. R1 to 5.5, R2 to 0.06. Feed fraction still 0.5. Run all. The Mayer-Lewis curve now sits near F1 equals 1 across most of the feed range. Early chain sections are nearly all monomer 1. Late chain sections are nearly all monomer 2. The drift plot fans out dramatically. Same feed, very different polymer. Two takeaways. The reactivity ratios are the chemistry. They decide whether you get random chains, alternating chains, or blocks. The feed fraction is the recipe. It decides whether drift sets in. For instructors, this module pairs well with a prediction quiz. Give the class R1, R2, and a feed fraction, and ask them to sketch the chain before running the simulation. For students, work through all 5 of the example systems in the module page.